Hello everyone, and welcome again to Niddle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and I would also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and today, following many requests from you, I decided to investigate the multivariate DCC, that is Dynamic Conditional Correlation, GARCH models. And we have already got plenty of videos on different types of GARCH models on our channel, so please check these out if you're interested in simple GARCH or some simple extensions of it like Gaussian mean or T-GARCH or anything like that. But today we are generalizing it to some next level. As you all know, financial assets are quite tightly correlated with each other, generally, and this correlation is manifested in both returns and volatility. And the most obvious case of two assets being correlated is perhaps the case of a stock and a benchmark of the particular market where this stock is traded. And today we have got just that. We have got 5 years worth of data for Apple stock returns and the S&P 500 returns. And we can study the interrelationships between returns and volatilities of S&P 500 and Apple using the DCC GARCH framework, the dynamic conditional correlation model that augments the logic of simple GARCH. And to start with, we can just calculate the average returns of S&P 500 and Apple on a daily frequency and average daily standard deviation and the sample-wide correlation of S&P 500 returns and Apple returns. And we arrive at the correlation of 0.67, which is quite a high correlation, meaning that Apple quite tightly reacts to movements in the overall market benchmark index. And as our starting parameter values, we will start with the constant volatility and constant correlation assumption. For the constant volatility assumption, just as in standard GARCH, we pick our constant mu across both the stock and the index to be equal to simple sample averages, our unconditional variance to be equal to just the sample variance calculated over here as the square of the sample standard deviation, our ARCH and GARCH parameters alpha and beta that code the immediate impact of disturbance on conditional volatility, and the persistence of the conditional volatility across time are set at zeros, so volatility is constant, it is independent across time, and the long-run variance can be calculated as unconditional variance over 1 minus alpha minus beta. And quite naturally, the starting value of the correlation parameter is picked as the value of the correlation coefficient across the whole sample, the sample-wide correlation coefficient. And now we can look at what the model returns if you just code in the constant volatility and constant correlation assumption. We can see that the beta of Apple is stable at 1.24, meaning that Apple is quite risky with regards to S&P 500. That's quite natural, Apple being a tech stock. And its correlation is flat at 0.67 across the whole sample period. And if we compare the dynamics of volatility across the GARCH model, the standard GARCH model, I have pre-coded on these two spreadsheets over here, and for, again, standard GARCH model, I've got a full video dedicated to it, so check this out if you're interested in that. But here we can compare the results of the DCC estimator of conditional variance, conditional volatility in orange. Right now they're flat because we have inputted the baseline constant variance coefficients, and the standard GARCH in gray. And we can see how those two interact and which is the best in proxy in the realized volatility in blue. And we can see notable spikes and relaxations of realized volatility consistent with the GARCH logic. However, we can also see notable co-movement of volatility for Apple and the market at large. So we can see that most notable peaks at market volatility coincide with the highest peaks in Apple's realized volatility. So can DCC provide us with some insight into why this happens, how we can code the dynamic correlation of Apple with the market in terms of volatility, and which mathematical and Excel tricks can we use to code DCC in Excel? That's by no means a straightforward task, so I would appreciate if you leave a like under this video. So for the DCC estimation, we again start with the constant volatility parameters, just copied from the previous sheet, and we can characterize our dynamic correlation by varying the value of the starting correlation value and parameters A and B. They are very similar to alpha and beta in variance persistence equation, but they here deal with the covariance matrix and the correlation structure of our two time series, of our two assets. And by the way, the whole logic of DCC is easily generalizable to more than two assets. You would just need to deal with longer vectors of parameters and higher dimension matrices of covariances, correlations, and variances. And here we can see that our correlation matrix QT, that then can be used to arrive at the matrix RT, that's actually the adjusted correlation matrix, so that all values are consistent with the economic sense of correlation. So all values would be between -1 and 1, it would be symmetric, the diagonal elements would be 1, all of this good stuff. Well, to arrive at that, we would have to first code the matrix QT, which would be different in every single day of our observation period. And we can see the resemblance it has to our conditional variance equation in the GARCH framework over here. First of all, we have got some Q bar matrix, which is just the starting and long run matrix of this correlation, and it is multiplied by 1 minus A minus B, very similar to how you find out your long run variance, isn't it, in the GARCH model? And then you adjust it onto the immediate disturbance. Those are vectors of residuals at a particular point in time, and this parameter A is analogous to alpha in GARCH, that is the immediate disturbance to correlation that is manifested in the residuals of your assets. And then there is some persistence in correlation through time corresponding to this parameter B. And then we can calculate the diagonal matrix of square roots of matrix QT, and that would be QT star, QT asterisk. So this is just getting the diagonal elements of this matrix. Everything else is zeros. So we can see that here we calculate the QT. The QT at the start is just Q bar, just as conditional variance at the start is long run variance for GARCH. From here, you can see this equation being implemented. 1 minus A minus B, so the parameters that are represented by these cells, times the Q bar matrix, which is calculated using long run variances and long run correlation values, and then the persistence parameters take care of the dynamics of this matrix. Then the QT star matrix is calculated at the diagonal as square roots of respective diagonal elements, and again you can generalize it to a 3x3 case, 4x4 case, and n×n case in general. And the remaining values outside of the diagonal are just coded as zeros throughout. And then, given the QT asterisk matrix or QT star matrix, we can calculate our dynamic correlation matrix RT, which can be arrived at by multiplying QT on both sides by the inverse matrices QT asterisk. And this is how it's implemented using the Excel logic. It's a bunch of M-mult operators, so matrix multiplication functions, and M-inverse, so inverse matrix functions applied to QT star. And we see that in the constant correlation and constant variance assumption that we have coded so far, our correlation of assets with themselves are always 1. That's what we want. That's consistent with the logic of the model. And the correlation of assets among each other, so this would be the correlation of Apple with S&P 500. This is a correlation of S&P 500 with Apple. They should be the same, and they're indeed the same. This is what is given by this mathematical representation. They are both equal to the long-run correlation, or the starting correlation value of 0.6733. We have just inputted the sample correlation over here. And then we can code our diagonal matrix of conditional standard deviations, dt. This would be equal to conditional standard deviations on the diagonal, and zeros everywhere else. So here, at the first day, we just return our long-run volatilities calculated over here by applying the square root of omega over 1 minus alpha minus beta logic, zeros everywhere else again, and then cross time, these are calculated as conditional standard deviations under this simple GARCH logic. And by the way, the DCC framework allows you to have the conditional standard deviation equations using T-GARCH, for example, or using E-GARCH, any other GARCH generalization. But here, for simplicity and as a proof of concept, I stick with standard GARCH for now. If you would like me to do a DCC with more assets, or do a DCC with a T-GARCH conditional standard deviation equation, for example, leave it in the comments. But getting back to the essence of our tutorial, here we have got our conditional standard deviation as the square root of conditional variance being equal to omega plus alpha times the immediate disturbance, which is the coefficient over here from this matrix we'll discuss in a little bit later, and beta times the lagged conditional variance from the past observation. And obviously here we see that we've got 2x2 matrices that are required to be calculated for every single observation day. So it becomes not entirely straightforward how to get from your usual time series representation over here with dates following each other and then returns following each other and so on and so forth to the DCC estimation. However, a clever use of indices will allow you to code that for any number of stocks, so any dimension of your matrices. And then you could return your DCC results, getting back the values you want using the index function from the estimation sheet. So this is the logic, and obviously the Excel spreadsheet will be available in our Google Drive as usual for you to look at it closer to get this idea of representation and construction of graphs and charts. So here, the immediate disturbance matrix, so you'll start at 0 because the lagged immediate disturbance at day 1 is just 0. You don't know what happened yesterday. But starting at day 2, this matrix would be a multiplication of a transposed vector of residuals onto the vector of residuals. And given matrix multiplication rules, multiplying a 2x1 vector onto a 1x2 vector gives you a 2x2 matrix. And it works for any dimension. N by 1 times 1 by n vectors give you an n by n matrix of immediate disturbances that can be easily accommodated in this GARCH logic for the computation of conditional standard deviations, and later on in the computation of log likelihood, which is the center point in how DCC differs from usual GARCH, or a sequential estimation of independent GARCHs across all assets that you are interested in. So now, having calculated the correlation matrix RT and the conditional standard deviation diagonal matrix DT, we can code the covariance matrix HT as the product of DT times RT times DT. And as those are symmetric, we don't need to transpose anything. We can just implement two matrix multiplication functions and get these three matrices multiplied together. And this covariance matrix is the major point in retrieving correlations, conditional covariances, and even dynamic betas of our stock. So stay tuned until the very end. We'll see how to apply DCC to get the dynamics, daily dynamics of betas for Apple. But before that, we need to know how to properly estimate and optimize all the parameters of our DCC model using Excel solver function. And to do that, we have to code this log likelihood function for every single observation, and it is quite similar to log likelihood function for your standard GARCH model, in that it uses probability density function of the normal distribution, but it uses a multivariate normal distribution, unlike the univariate case that is used in simple GARCH. So here, you need to take the natural log of the determinant, so the matrix determinant of the covariance matrix HT, and also add the disturbances times the inverse of the covariance matrix HT over here. And it can be implemented using the formula just like that. So we multiply -1/2, so standing over here in front of the brackets, onto the if-error function. If-error function, just as in our previous videos on GARCH models, allows us to use fewer explicit constraints on parameters so that the model knows when the model is unstable and that it would return an error, so it should use other values of the parameters that are consistent with the logic of the model. But apart from that, we just have n times natural log of pi, and n here is the number of assets, 2 in our case. If you do a 4x4 or 5x5, it would be 4 a natural log of pi, 5 natural log of pi, and so on and so forth. Then we add a natural logarithm of the determinant, mdeterm function in Excel, of the HT matrix, and then we use this complicated matrix multiplication logic to get our residuals and the transposed residuals multiplied onto the inverse covariance matrix over here. And that returns our log likelihood for a particular day, and applying it for every single observation day in our period, we can get our total log likelihood as the sum of the whole column. And finally, we can apply solver to maximize this log likelihood by varying our parameters. And let's discuss which parameters we are allowed to vary. So obviously, we can vary our vectors of standard GARCH parameters. So we have got 2 constants, 2 unconditional variances, 2 alphas and 2 betas. So B2 to C5 is quite straightforward. Then we are also allowed to vary the starting correlation parameter, which would also be the long-run correlation parameter between Apple and S&P 500. And for a 3x3 or a 4x4 case, you would be allowed to vary starting correlations for every single pair of your stocks, or assets, or time series in general. And then we can also vary the A and B parameters that describe the dynamics of our conditional correlation. And the only restriction we need to input, simply because we have saved upon a bunch of restrictions by using the if-error function in the log likelihood, is to require the B11 and B12 cells, that is, dynamic correlation parameters A and B, to be non-negative, because negative parameters can be consistent with the logic of the model. However, they would be quite hard to interpret from an economic point of view. So we require them to be non-negative for the model to be interpretable, and we click solve while making sure that we have unticked this box over here, because we can allow constants, for example, to be negative, or the correlation to be negative, why not, and using the gradient descent algorithm, GRG non-linear. So we click solve and wait until the algorithm converges to the optimal solution, and it can take some time. And in less than 2 minutes, the solver algorithm has converged to the optimal solution. We can see that our value of log likelihood has increased quite a bit from the starting value, and our parameters have changed to reflect the optimal solution. So first of all, we can see, as usual, the variance dynamics of S&P 500 and Apple are quite persistent, with the sum of alpha and beta being around 0.9, and the GARCH beta being around 0.7 or 0.8, quite typical, and the starting and the long run value of the correlation is around 0.6, lower than the sample estimated value of constant correlation as 0.67, meaning that there are high correlation episodes and low correlation episodes, and in the long run you should expect Apple and S&P 500 to be correlated at around 0.6. Then the dynamic correlation parameters are actually positive, and we can see that correlation is quite persistent, with the persistence parameter being 0.67, but not as persistent as individual variances. However, these values are quite comparable. And let's see how did it change the estimations of conditional variance dynamics. Is it different or much different from the standard GARCH estimates, and what else can we derive from our DCC model output? So we can see here, if we compare the orange lines of DCC estimated conditional volatility to the gray line of standard GARCH estimated conditional volatility, we see there is not much difference here. Well, it does capture the peaks and troughs marginally better, especially when there is core movement in the market dynamics and the stock dynamics. So for example, over here, we can see that it captures the trough and the peak better. Here it captures the trough, and here it captures the trough and the peak better. But the difference is not monumental. Using DCC for volatility modeling is more computationally intensive and not markedly better than standard GARCH. However, it's slightly better. So it should give us at least some idea into whether to apply it or not, whether we want to estimate something very quickly and a little bit less precise, or much more thoroughly and a little bit more precise. However, the main interpretative and explanatory power of DCC is the dynamic correlation and dynamic beta. So for the dynamic correlation, we can see that obviously the correlation coefficient of Apple and S&P 500 does fluctuate around 0.6. However, there are episodes when correlation reaches as high as 0.9 and as low as 0.15 or 0.2 at some points, meaning that, well, correlation cannot be assumed constant across time, and DCC logic accommodates for that, allowing you to model the risk of your portfolio. For example, if you have many stocks there and you want to figure out how they are correlated to S&P 500, making this logic more applicable. And also, as a nice bonus, we can also retrieve the dynamics of daily beta of S&P 500 using this well-known formula that represents beta as the ratio between the covariance of stock and market returns and the variance of the market returns. So here, for example, we can see this logic applied. The covariance of the stock return and the market return is just correlation times the two standard deviations, and the variance of the market return is obviously just the standard deviation of the market return squared. And we can see that beta does indeed fluctuate around 1.2, 1.24, which was the sample estimated beta. However, at some point, it does reach as high as 2, and sometimes it falls to as low as 0.4. And this is very important to model required returns, to model the risk of your portfolio, and to see whether the asset you're investigating has hedging properties or safe haven properties. That is actually a video I have already recorded, so please check this out. However, DCC allows you to model these properties way more rigorously by looking at when exactly does the beta or the correlation coefficient reach its lowest or its highest. If the correlation coefficient is its highest when the market goes down, then it's bad news. This asset is very poor at hedging and will expose you to a lot of risk on the downturn. And if the vice versa is true, if the correlation coefficient is the lowest when the market plummets, then it's good news and your asset can actually serve as a decent hedge or at least a diversifier. And that's all there is for coding your own DCC model in Excel and interpreting its results for the dynamic correlation and the dynamic beta of a stock. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions on videos on finance, business, or economics topics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.